Okay, good morning. Thank you all for coming. And I know even though this is the first iteration, so to say, of this conference, it really has a pretty high quality in talks. So I just looked at the schedule and said, okay, if I didn't have to go to my own talk, I probably knew that I would go somewhere else. But I'm glad you all came, and despite all the options that you have. I just thought there was a bit of a room change. I don't know when this happened, but when I looked at the schedule the other day, I think I was still in room 10, and now it's room 2. So just to make sure, everyone, this one is about containers. And yeah, as nobody's leaving, I think you came for that purpose. All right, so I think some people are still walking in. So I'm going to start slowly with the introduction. My name is Matthias. I come from the bordering country of Germany. In Germany, let's start from the bottom. I teach at 2 universities in the area of Stuttgart, mostly in the field of modern distributed systems and modern software engineering. And there's something new on my intro slide. This is here on top. I work for a company called Novatec, but we as Novatec just recently got acquired by CGI, which is probably famous here too. They're sponsoring also this conference. So it's kind of funny because when I applied for this conference, I didn't know about that. Now that I got accepted and do my talk here, I saw that they are also around. Is there anyone from CGI in the? Oh, hey. Front row seats, very good. So hi to my new colleagues here. Also, there is a booth. We have a booth. I might actually go there later and be there around as well. So please come over and say hi to my new colleagues. Now, I'm going to move on. So what am I, for those who don't know me, so a quick introduction what the contents of my daily business is, like what it was and what it's hoped it's going to be in the future. So I develop software, I help in software engineering and architecture to make our clients happy. That basically involves things like building good code, run the things on modern technologies, and of course, kind of automate all the things and make it work right. And in a lot of the aspects, I mean, you probably have seen something like that before. And in many aspects of this kind of chain, containers play a very essential role. So I'm working with container technologies a lot. And so for today, it's mostly going to be the part in the kind of build step to focus a little bit more on how can you actually build container images. I mean, this might probably sound like a solved problem to most of you, because I guess everyone has heard of the thing called Dockerfiles. But funnily, it was just today in the keynote by Sander this morning. Who saw the keynote this morning? Okay, so good. He made the example of referencing a problem that root caused in the area of a Dockerfile. So apparently it is still a hot thing, and I hope I can tell you a couple of things that you don't know yet in this field. So besides Dockerfiles, there are plenty of other options to actually build containers. I might not have to talk to introduce all of them to you, but I try to give a bit of an overview. And in the end, my idea is to say, okay, what can we kind of learn from the various approaches, and how could this help me to improve, hopefully, my own container build process? So it's not that I want to point out, well, this is the good one and this is the bad one. They all have their strengths and weaknesses, and we're going to have a look a bit over that. So if I talk about strengths and weaknesses, we can also say, okay, what does actually help making a container or a container build process good? So this could be, of course, like how fast is actually happening, how big is the image, how good is the configuration, is it well structured, is it secure? And if you want to optimize all of those things, of course, is it still kind of simple? I mean, of course, you want to have things simple, because writing Dockerfiles is probably, or like building containers is probably not the most exciting thing software developers will do, but it's certainly something that they actually face in their daily business. And I hope I can make things as easy as possible for you. All right, I think I'm going to go over this quickly because I guess everyone knows what a container is, but understanding a bit of the technical background also helps to understand what actually can improve your build process. So basically, a container is an isolated process that comes along with all the libraries and dependencies that it needs to run. So it's like a kind of a self-sufficient component that has everything that it needs. And this is like an isolated process being isolated by terms of a low-level Linux functionality, like namespaces, change root, and C groups. Those things people normally don't know or don't understand, and the good thing is they don't have to, because like there are higher-level abstractions like container daemons that help with that process and provide a simple API to deal with those containers. An image, the thing we're going to look at today, is kind of a template or a blueprint to instantiate such a container. As this is very much about Java, you can also say, okay, maybe this is the class, and then later on container will be the instantiated object. Important to know is that those container images are not coming as like big blobs of data. They're actually like being structured into layers. That means that a container daemon can use the individual layers and like kind of combine them. So if you have overlapping layers in different container images, the container daemon has to load it only once. And that's something you can certainly like consider for using in your improved build process. So in this example, it's like an old, very old kind of diagram where you can see it's always a transition between an image and the container. So the image is the immutable artifact. If you instantiate an image with run, you get a container. With a commit, it goes back to an image. With run, you can instantiate it again and put new things on it. And every like addition to it comes as a new layer. Like longer time ago, the containers images were really built like that. But it wasn't very long. So Docker came out in March 2013, I think. And in May was the first time when actually that term Dockerfile was mentioned in the history. So again, this is something I expect most people to know. So a Dockerfile is kind of let's say a batch execution, which is processed sequentially, which kind of constructs, or it's like a construction plan for your image. And I mentioned those layers before. So each line in a Dockerfile results later on in one layer of your container image. So in this case, I have a base layer with the Ubuntu. Then I have this Java layer that I do with the apt install. Later on, I'm going to copy my jar file in, and then I'm going to tell with the command whenever somebody instantiates this container, this call will be executed. So that's the way how it works. And actually, the majority of Dockerfiles doesn't go much beyond this complexity. So even if you look at the Docker Hub documentation of, for example, the Eclipse Tambourine image, this is kind of the documentation that you get. So just as I did now, you have a base image, you create a directory, you copy the jar file in, and that's that. And to be fair, it works, but there are certainly some things that you can improve or like improve in different ways than what is given in that documentation. Right, so this is the Tambourine example. You can also cut it down to 3 lines and just copy the code in a very simplified way. So the first step that you actually have to do, especially in the Java world, is figure out which is the right version and which is the right distribution. So there are basically base images for all the different distributions, and this is a part I'm not going to go into. There's a really good talk from my friend Garrett about JVM landscapes and what the different distributions do. They all come with base images, so if you want to go further into that, please check out this talk. I mean, you just Google for Devox and Garrett, and I think it's going to pop up pretty quickly. All right. The Dockerfile evolution, however, did not come to an end or wasn't like, didn't stay like as it was in 2015. In 2017, there was an announcement for so-called multi-stage Dockerfiles. It kind of kept the same approach to do things, but as the name says, it kind of dissects a Dockerfile into multiple stages. Each of them will result in an own image, but most likely just the final image is something that is of interest to you. So basically, it means you can say, I want this part to be done in a container, I want this part to be done in a container, and I take the results of it and put it into the final image. For example, what this helps you is also to put a bit more of standardization process into your build of the Java application. So if you look at the previous files, those files kind of expect an already existing jar file. So this kind of leaves it open. Where does the actual source code come from? How is it built? Where is it built? Which version have been used? And so on. So it's a certain factor of insecurity there, because you don't control that step. With such a multi-stage Dockerfile, you can certainly define and say, okay, I want here, in this case, Maven, the 3 image with the Tamarind 2021, and whenever the code is going to be executed, it's always going to take the same build configuration. So there's no kind of variance or options to make it any different, and that, of course, increases the degree of standardization. So it's going to copy the code in, it's going to compile it, it's going to result in a jar file, and the final run image has the same copy step as before, but it's taking the jar file as a result from the first stage and then copies it in. So if you do something like that in a pipeline, it of course means that you make sure by using that Dockerfile, it's always going to be built under the same conditions. So this just highlights it in a bit more colors, and the processing sequence just stays the same. And this basically means you declare the first stage with a certain name, and then the copy call, you declare, okay, where is actually this coming from? If you omit that, it will try to copy the code in from your local file system. All right, at this point, the Docker evolution didn't really come to an end. BuildKit was a technology introduced in 2018. It was in beta for a while, but this is like the standard of Dockerfiles or the Docker build engine that we're using today. This brought a lot of things in, like smaller images, better flow logic. So they addressed quite a couple of things where you could say, okay, I want to run some stages in parallel that are not dependent on each other, and copy and move things around, execution flow. However, this also kind of turned Dockerfiles into a bit of an own programming languages, which certainly doesn't help for making things a lot simpler. Anyways, one of the cool things that it brought in was actually the possibility to use a cache. So, of course, in containers, you can create volumes and basically get out of the container and interact with the local file system. But up till this point, this wasn't possible with Dockerfiles. So during the build process, you didn't have that volume mount option, which came in there. And that certainly means if you do those build steps, like in this case for Maven, but you can also imagine NPM or whatever, you can basically mount your build cache, and then it's not going to be re-downloaded whenever executed. Of course, this kills a bit the advantage of consistency, because it kind of takes things from the outside, from an unknown source. But it's certainly something I would recommend in development, because if you leave that out, then like the Maven build or package or compile process will always download all the libraries again, because it's always a fresh container and it doesn't know like there has been things happening before. All right, so if we look at the evolution, we already have a bit of an idea of the criteria to say what can make a container better or worse than others. Of course, simplicity, I mentioned that, but that is kind of contradictory to like optimizing in speed, in size, in structure, security, and so on. Especially with Java, you have the additional criteria, how easy is it to apply JVM configuration. In reality, the documentation still looks like this, and that's why I said, okay, probably we can do things a little bit better as it is displayed here. Now, what I have noticed when talking to a lot of people about how they optimize their build process, they said, okay, if an image is smaller and doesn't have a lot of things in there, it's probably less vulnerable, because what's not in there cannot be exploited, which is absolutely correct. And also, it makes the image easier to move around. But it's, in my opinion, not such a good idea to basically like squeeze out the base operating system layer. Because, as I said before, if you use that layer consistently across multiple different images, also around multiple different, let's say, programming frameworks, the daemon has to load only once. So you can't really optimize there much. But if you have multiple different base operating system layers, it basically decreases your performance. So I would say go for consistency rather than optimization on that layer. Also, this layer doesn't change very often. So if you don't, I don't think you will exchange your base operating system every week. But what's going to change very often, if you do repetitive builds, is certainly the application layer. And it might make sense to focus a little bit more on that, especially in the world of Java. You saw the example before, it's just a jar file that's getting copied in. That means it's always the same big kind of blob of data. It's a zip file underneath, but for the container layer, it's just like one big file. But inside of such a jar file, you have dependency jars, resource files, and on top, the class files. So the same principle applies there. If you rebuild your jar file often, it's very likely that your class files change often, but the dependency jars probably not so much. So what you can apply here is this option of extracting your jar file into different segments. So you see here there's dependencies, Spring Boot loader. This is obviously a Spring Boot example. So with every of these copy steps, you basically create a new layer in your final container image. That also means if only your application changes, only this one needs to be updated in a repetitive build, and that certainly brings a bit of optimization, especially if your applications are larger. Then, if you apply the two things that I said before, you can already see there is optimization, but it makes things more complex. So first I have a build stage, then I have this extract stage, and I finally have a run stage with a very granular structure of my Java application laid out in this image. And I have additional kind of an entry point configuration if I want to tweak any things in my JVM configuration. So this is probably a bit more advanced than what we have seen before, but you can do even more. So I think with Java 9, the module system was introduced. And with the tools of jlink and jdepth, you can actually improve the layer of your JRE also in your container. So let me walk you through this real quick. So on top, we start and take again a Tamarind image as build image. And then with this jlink command, we create a custom Java runtime. So you can ignore most of the command line switches. The important one is this one of adding the modules. So you can basically specify which of the modules of the JVM do I actually need for my later on runtime. This will be given output here on the Java runtime, and later on, this one copies that runtime into your final container. So you need a base operating system layer, then you put the Java runtime in, the custom one, and later on top, you put the application. In this case, I didn't split it into components, mostly for the sake of space there, but of course you can apply that too. With the combination of jdepth, you can even automate this process. Like with this step, I added the module because I knew which module it's going to be. If you have different jar files, they might have different requirements for the modules within the JRE. So with this jdepth command, you actually pass in your jar file, and this will, as a result, spit out the list of modules that your JRE requires. And then in combination with that jlink command, where you feed that info in. So that means this will basically combine the live results of what the jar file actually requires, and then build the custom JRE out of that. And then finally, of course, put it in your later run image. Again, this doesn't make things simpler, but it certainly helps on optimizing here. All right, before I go there, I probably want to show a couple of things live. So I make this a little bigger. Just for the back, is that file readable in the back? Is that okay? Okay, good. So what I have here is a very simple application. It's just like a Spring Boot REST application that exposes like a few single endpoints. And I have a lot of Dockerfiles. So your repositories should not look like that. This is just for demo purposes. You should only have one, or maybe not have anyone at all if you use other tools that we're going to look into later. But I just want to do a couple of steps to compare the things live that I had shown before, if the network likes me. So let's check. I can say docker build, and I'm going to start with a simple one. So, for example, this simple Tamarind image that I referenced a couple of times. So I'm going to say -f. This will basically pick hopefully the right file. And then I'm going to specify a tag. I'm going to say in Amsterdam, so it's the AMS app. Simple Tamarind. All right, so this one came pretty quickly because, as you can see, it used the cached mechanism. I did the build before because I wasn't really exactly sure if I could rely entirely on the network, but just imagine this would have been a fresh build. So what I have just created is that simple Tamarind image. And if I look into it and say Docker history, and so I can type AMS app. I don't like so much typing. What you can actually do, I'm not sure if you're aware about it, you can pick just a few characters of the image ID, and Docker is smart enough to resolve that. So this is going to show basically the layered structure of this image. A lot of those layer information is missing because that's like from the previous build of the actual underlying base image. But the ones on top, right here, I can see that. So this is like when I copied the jar file in. So the jar file in this case about 23.3 megabytes. Down here, this is probably the base operating system. This is probably the JRE. And so this results in an image of 335. Now, what else did I show? How can we make things better? I can do a multi-stage approach. So in this case, the Dockerfile was totally relying that under target, there is this jar file. If this jar file isn't there, the build would actually fail. And the Dockerfile doesn't validate where this jar file is actually coming from. So if I use a multi-stage approach, I'm just going to use that command again. So I'm going to say multi-stage builder. I think this is the simplest one. So yeah, this one actually builds the code and then copies it over. So I'm taking. So what you can see now, it's basically copying, first of all, downloading, and then it's copying in the source code, and now it's going to do the Maven invocation. And as it doesn't know, like it's like the first ever invocation, it will download all the necessary dependencies. So the network likes me. This was in 13 seconds, but as you probably have done in Maven builds before, you know this will always repeat in that way. So even if I go into that code file, and I'm going to change something here, just like the method signature, and I'm going to repeat it, it's going to go there again. So it needs to download everything over and over again, and depending on the size of your application, that might be a bit painful over time. So approaching with this cache, that means it's going to mount the Maven cache into that build step and can reuse things that have been built before. So I'm going to jump into this and say cache. So probably for the first time, okay, you can already see it's a lot faster because it didn't download all the things. So even if I go in there now and say, okay, I'm going to change something again, I'm going to call this whatever, hello Amsterdam, and rebuild it, this is going to be super fast. All right. The next optimization I talked about is this layering approach. So I'm going to do this one next. In this special example, I'm just going to copy the jar file in. I'm not actually building it, but of course, as I said, you can easily combine those. So, and just for the reference, if I do Docker images now, we see that multi-cache and the simple one, they have exactly the same size. So things didn't get any optimized in any way. Also, if I say Docker history and pick this latest one with the A29 here, then we'll also see the jar file is just basically copied in as one single layer. This is hopefully going to change if I do the multi-stage layered version. So I'm going to call this multi-layered. And again, it used the cached layers, but down here you can now see we have those steps of copying that decomposed jar file in. So if I do a Docker, first of all, the Docker images, it still has the same size, so no surprises there. And if I say the history here, so this means now I have those layers individually. And you can see from the 23.4 megabytes that we had, 23.1 is actually dependencies. And 6.1 kilobytes is actually just the updated code. So this is basically the only delta that needs to be replaced when you redo the build. So that can certainly have a bit of an effect. And finally, what I wanted to show is that jlink approach. So I have two examples here. This is the jlink with a bookworm. This is like a Debian image underneath. So you can see here I'm taking this bookworm slim, where the JRE will walk in and then later on the code. And I have another one with that Alpine image, which is even which is even smaller. So let me try that. I'm going to say Docker build jlink bookworm. Okay, this is not incorrect spelling, but it doesn't really matter now. So you can see now it invoked JDEBs, which basically returned that that file, this debs info, which jlink then uses and creates that custom JRE. So if we look into Docker images here, you can see this is quite a bit smaller with 184 megabytes. So if I go in there now and say Docker history E4E, then we can see it's still the 23.3 part for the application, but the custom JRE right here is pretty small with 63 megabytes. So that definitely is an optimization. And also, of course, on the viewpoint of security, not just on the size, but again, what I said before, what isn't in an image cannot be exploited. So use standardized components, but use as little as you can, or only as much as you need. And that will hopefully save you some blood pressure in the end. So if I modify this one and say, okay, we're going to pick the Alpine version now, and say, this is jlink. Okay, you can see I'm doing this all live because I'm not doing all the typos. And I repeat Docker images, then you can see this one was even going below the level of 100 megabytes. And if we look into it, of course, the custom JRE is going to stay the same. Okay, it's a bit too short. The custom JRE is again 60 megabytes, but the Alpine image is really small. So this image mostly just consists of the application, the JRE, and a minimal base image. And that's pretty much how things should be. All right, now I'm going to show a few more things, but I'm going back in the presentation a little. Or maybe I can show this here. I created some file, I think I called this ultimate, where I put all the things in. So basically, using the mount cache, doing the build, then decomposing it, and finally modifying the Java version, even change the user. So the Dockerfile almost gets up to 50 lines of code. This is kind of what it takes if you want to apply those things. I mean, you can just leave those ones out that you think are not relevant for you, but if you want to do it, that's kind of the price that you pay. What we can take away as learnings is for the base image. I mean, in my personal opinion, it doesn't matter much if you use an Alpine or an Ubuntu or Debian here. As I said before, the important thing is keep that consistent. I mean, avoid wild growth, that every team picks an own base image, because that's going to end in nightmare whenever a vulnerability comes up. So if you go on the news and say, okay, there has been this exploit, Log4j, shell shock, heartbleed, whatever they're going to be called, the first thing you're going to do is run around and try to check where am I affected at all, and if so, where would that be? And if you have consistency on the bottom of your image stack, then you can quickly say either all of them are affected or none of them are affected. And that will certainly help you in patching that and getting back to production. On the layer of Java, use jlink and jdapps to customize your JRE. Make this only as small or as big as you need it. And on the application side, separate the build and run stages and try to apply this layered structure. At least from my experience, these are the steps you can do to improve all that. If you have anything else, feel free to let me know. Then, this took like half an hour for all the Docker stuff, so I have 18 minutes for the rest. The good thing is the rest is a lot simpler. So I'm going to skip this timeline. This shows a couple of things, how when Heroku and Buildpacks came out, when containers were standardized to the OCI format. If I have more time, I talk about it. Today I'm going to leave it out. So chip is a technology originally coming from Google, which is basically just doing one thing, creating container images out of, let's say, JVM-based application languages. So, of course, this will work with Kotlin as well. And it works as a Maven or a Gradle plugin. So the interesting thing that you see on this slide is the part that you don't see. Because for this, you don't need a Docker daemon. I mean, normally if you build images, in particular with Dockerfiles, they're going to be run and committed, and you need a Docker daemon to do all those executions. In this case, the code for the image is directly generated from that plugin, and you don't require a daemon. Especially in some, let's say, older build pipelines, this can be very helpful if you have build nodes and you have certain restrictions where a Docker daemon might not be able to be installed. This makes your life a lot easier there. In the end, you can export the results either directly to your container registry. You can, of course, build against a daemon if you have one. So you can put it into your local registry, or you can also export it as a tar. Chip automatically applies this concept of the layered structure. It detects the jar files and dissects it, and basically puts that into your final image. This one normally goes pretty quick. I just don't. So Google chip. So it says container tools chip. And if you go in there and I think, no, this is not what I wanted. There was a simple example. So you basically just say Maven compile, then you specify that plugin right here. I mean, you can of course, put in your POM XML, but just I wanted to show you all the things from scratch, and nothing has been set up in the back. I'm going to copy this over. This and say. So there are some different ways to do it. You can say build, you can say Docker build, and you can say something with a tar to export it to a tar. I'm using that Docker build so that it shows up in my local registry. And I'm going to say, I think that's the way how it is. All right, so it's compiling the code, it's building something, and it comes back pretty fast. So it's just one line of code invocation, and of course it can use or reuse the same Maven cache. This one, of course, builds now locally on my machine, but you can certainly nest this in kind of multi-stage files, as I shown before, but of course then you require a daemon. So if I look at Docker images, we will see something funny. This app has been built 55 years ago. So I know we just built it last minute. The way why this happens, and we'll see this later on with the build packs, they set a standard time. So I think this one is actually the Unix time where it is set. So all the images have the same timestamp. Why do they do that? Because the timestamp in a build step is normally also taken into the ID of the container image. That means if you do two identical builds into different environments or at different times, they're going to have a different ID, which shouldn't be the case. Or like if you have the focus on consistency, it shouldn't be the case. That's why all those chip builds will be pointing to the same point in time. You can unconfigure that, but then basically you sacrifice that consistent image ID. Anyways, we can see this has about 310 megabyte, and if we look into it, AMS app chip. History. We can see that this plugin also automatically splits down into dependency, resources, and classes. So all the steps that we have kind of built manually before automatically comes out of the box here. And let me just try one thing. To also, I need a password. So I'm trying to push something to my local. I hope this doesn't show in clear text. No, it doesn't. Yeah, I can still edit the recording probably. But so if I take this out and just say build, and what I need to do, I need to give it an image tag which is bound to my name, so something like that. And now it should run. In the meantime, I'm going to log in here real quick. And it's already there. So you can see less than a minute ago, this was just not only built, but directly pushed. So again, this simplifies a lot of the steps you might be working with on a daily basis. And if you just say limit to the JVM world, then this is certainly worth to give a try. All right, now I'm going to finish things here with build packs. Now, build packs actually have a history which are older than containers. So they come from the very early idea of PaaS, like platform as a service, where the PaaS claim kind of was from Heroku and Cloud Foundry. You give us the source code, and we do provide everything around. So we're going to build it, we're going to scale it, we're going to run it, we're going to do everything fine. But in order to do that, they needed a mechanism to be applied to a set of different programming languages or frameworks. And that concept was called build packs. So a build pack would detect what kind of an application is it, it would build it, and export it into a thing which was back then called like a runnable. Today we'd say probably a container image, because it's a very similar thing. So Heroku came up with it. It was kind of incorporated in Cloud Foundry, and then again in a later version at Heroku. And then just after that, there was this big hype wave of Docker and Kubernetes and all the containers in the world. And suddenly the build pack people realized, so that step that we're doing inside of a platform is now actually a step which a lot of people would benefit from. So they started the Cloud-Native Buildpacks as a CNCF project, which is kind of the reference or definition of that this architecture. And there are different implementations. I mean, there's one from Google, there's one from Heroku, there's one from Paketo, which is actually coming from the Cloud Foundry people, and you can build your own ones. I mean, if your company is large enough, and I've done that in some companies, started building your own build packs, and then you can really streamline your image build process, and can take a lot of benefits out there. So how that works, this one doesn't work without a Docker daemon. It totally needs that because it downloads this so-called builder image. This builder image contains all the detecting mechanism, the lifecycle, all the potential build packs, and you have a CLI where with one command you can just kick that off and it will result in some kind of an output. So I can show that here real quick. So the command is called pack, and I just say pack build. Actually, I can say packs just builders. And then these are the standard builders that you can point to. So there's, as I said, something from Google, from Heroku, from Paketo, and all those build packs come with a list of languages that they support. So this certainly goes beyond Java. This starts, of course, making a lot of sense if you have a diverse and a polyglot application landscape. And the one I'm currently pointing to as my default builder is this one. So this is what I specified before. And now I can just say pack build, and I'll call this AMS app.paketo. And compared to chip and also Dockerfiles, this is pretty verbose. So you get this, what they call the bill of materials, all the things that are happening in there. So first of all, the detection mechanism. These are the build pack that the mechanism identified to be used in the final image. Then it's going to walk through pulling like the JVM, which has just been downloaded now. And again, the first iteration takes a bit because those layers haven't been cached. And then it's going to construct a final image. So I'm going to move on in my slides while this is still executing because of time issues. And why can this be so helpful? So in the beginning of this talk, I told you that most often images change on the top, which is still correct, even half an hour later. But sometimes you might also come to the situation where you don't want to change on the top, but you want to exchange something on the bottom. And this is exactly the situation I mentioned before when certain vulnerabilities come out. When you say, okay, my base Ubuntu or base Debian image has this exploit and I need to do something. And for this, build packs have this so-called rebase mechanism that can take your existing image, or even more valuable, it can take many of those images and just rebase it and build new images with an updated base layer. That, of course, makes a lot of sense, as I said before, if you're not bound to only one language, because then you can kind of control it easily yourself. But if you use multiple of these. I do this experiment every year with my students in the distributed lecture class. Say, okay, we built a polyglot application that does the same thing, but in different languages. And you kind of are responsible to come up with a Dockerfile. And if I have 20 different frameworks, I just found out I also have 20 different base images. So that's pretty much what the reality will also be in I think in a corporate company, if you give the freedom to do so. And with this, you can certainly narrow down this vector of attack by saying, okay, we only have one. So if exploits come out, I think when the log4j exploit happened, companies that used Cloud Foundry and are using those build packs, they were operational again within minutes because they just could say, we're gonna rebase exchange all the images and restart them again, and we kind of make sure the exploit is not going to happen in any of our systems. Right, so that's the stuff I showed with pack. Going over here again, so this has now finished. If we go and say Docker images again, we can see this is like 10 years younger than the chip image, but still old. If I do a Docker history here, I go say 827. I see here this application is also sliced into different components, and like I think this top slice right here is the actual the class files, and the dependencies right here below. So yeah, it also creates a bit of like nicer outputs in the layer documentation, so you can get a bit of an idea what is actually happening in there. And as it took so long on the first iteration, I just want to try to show you this isn't always the case. So I'm just going to say hello AMS and rebuild it. And with this iteration, it should have most of the things cached and reusing it. As you can see here, this has skipped this in the initial part. It's just going to do the build and then detect, there's not much to update in dependencies, and we'll come out with the final layer. It's probably not as fast for such a small component like chip or Dockerfiles, but it's kind of neglectable if you repeat that often, especially on larger components. All right, so 3 minutes. The thing that I showed before with jlink and JDEPs is actually also applicable to Buildpacks. I mean, I just used it in the plain version. I said pack build, then it's taking all the defaults, but it is configurable. So if I say, okay, I want this Buildpack JVM jlink enabled, then it's going to apply the same functionality under the hood. So it's going to only add those modules to your JRE that you actually require. And this can, of course, make the image a lot smaller, like what we have seen in the Dockerfile example. If you happen to use Spring Boot, then you don't actually need pack. You can also reference this Buildpacks with a Maven or Gradle plugin, but again, then the build will happen outside of your final image. So with pack, everything is just like scoped underneath. Right, so last 2 minutes. First of all, who heard something new today? Okay, that's good. That makes me feel better. And yeah, again, I wouldn't say there is this one solution which is better than all of them. The importance, I guess, is that you can say, okay, I'm aware of the options and I'm aware of the sub-possibilities of that options. And as a base recommendation of this will always be true, say, okay, keep your base image as consistent, layers as consistent as possible, especially looking at it from the bottom. Avoid wild growth that can easily happen through Dockerfiles, and automate and standardize as much as possible. Try to give those technologies a try. I mean, they're all open source and you can easily try them. And I'm always struggling with such an assessment, but I just try to kind of say where I would see certain advantages in comparing those things. I mean, especially it's difficult because Dockerfiles have such a broad scope. I mean, in general, you can do all of those things, like all the advantages that I showed in Dockerfiles, but then it's going to certainly lose on the factor of simplicity. Chip, in my opinion, certainly wins in the factor of speed and simplicity, but then is narrowed down to like JVM components only. This is where the advantage of Paketo comes in, but then this will kind of, I mean, with simplicity, you should potentially take into account you're depending on an additional component. But this is as much as I can summarize it. If you have any feedback or questions to that, you can certainly ask me. The examples that I've shown are in this Git repo, and also like a little documentation of all the steps that I've done. So if you want to replay that for yourself, you can certainly look into it. There's also a dev container specification, so you can easily just run that in a code space and don't need to mess up your local environment. All right. So I haven't updated this to CGI, so I'm sorry to my new colleagues, and I didn't get a hoodie yet either, so I'm still presenting in my old clothes. If you want to get in touch with me, feel free. As I said, you will find me in Blue Sky or on LinkedIn. And time is up, so I just want to say, before I open up for questions, I would first of all say thanks for listening and coming by. Do we have time for questions, or should I just... I mean, I'm going to be here, and I'll go to the CGI booth if you want to find me. You can find me there. I probably have to leave at 4 to catch my train, but I'm going to be around if you have any questions to me. Thanks.